so now we're going to convert something in the time domain into the phasor domain. So you've probably heard those words before, but if you were like me, the words that were said sometimes didn't actually like enter into my brain until later, and then it's like I heard them a lot, but then it's like it was too late. I didn't really know what they were, and then I was like, I had to go way back and figure out what are they talking about. And so I don't know if that ever happens to y'all or not, but you've probably heard time domain and phasor domain. So what that means is time domain just means regular functions as a function of time. So the current as a function of time. And that is the world we live in. We live in a regular world where time travels forward and all that. But these are very difficult to deal with because they're trigonometric functions. And trigonometric functions are hard. And it turns out that they are easier to deal with as complex exponentials. And complex exponentials, as we just learned in the last problem, if I have e to the I theta, that has a cosine part and a sine part. And if you just take the real part of that, and that represents the real world, but you can work with it in the complex world and then just take the real part back out. So you take the real part, you stick a complex part on it, and then they're exponentials, which are easier to work with. It's a lot easier. Remember how in calculus when you had e to the 2x, that's the best function to have in calculus because it's e to the x is its own derivative and its own integral and all that. They're just easier to work with. And trig functions are not. And so that's why we use complex numbers in electrical engineering and in physics until you get to quantum mechanics when things really are imaginary. And that kind of blows my mind. You can't do quantum mechanics without J. But anyway, so we're going to change these into their complex part so that we can work with them easier. And then when we want to get back the part that's in the real world, we'll put it back into the time domain. Now, we need to decide whether we're going to work with the cosine part or the sine part. And by convention, we usually work with the cosine part. So the cosine part, if you remember cosine theta plus j sine theta, the cosine part already is the real part. So that's useful. And so we want to, if we have something that is sine, we want to change it to cosine first. And so unless you're like me and I tutor the trigonometry class a lot, you probably don't remember all of your trig identities. But one of them is that sine theta equals cosine theta minus 90 degrees. So all that means is if I have a sine graph, if I shift it, if I take a cosine graph and I shift it to the right by 90 degrees, it lines up with the sine. I mean, cosine and sine are really the same, they're just shifted. So anytime I have a sine, I want to change it to cosine. So the first thing I'm going to do with this is say it's 15 cosine 200 pi t plus 45 degrees minus 90 degrees. Now at this point, if I end up with a degree measure that is bigger than positive 180 or smaller than negative 180, then I'll add or subtract 360 to get it into my plus 180 and minus 180 range. It's not that having a number like positive 190 degrees is wrong. It's just you can't then compare that. Everybody's not going to have the same answer. To make sure that everybody has the same answer, we want this to be between negative 180 and positive 180. So you would subtract 360 and you get negative 170 degrees, and then we'd all be agreed that we have the same angle. Okay, so this becomes 15 cosine 200 pi t minus 45 degrees. And then as a phasor, this is 15 angle negative 45 degrees. And so then you might be asking, well, what happened to that 200 pi? Well, it didn't go anywhere, and it still is part of the function, but it's not going to play a role if I am adding and subtracting this to other phasors that have the same frequency. If they all have the same frequency, then I can use them together. But where it does come into play is when I start changing my inductors and capacitors to the phasor domain. An inductor is J omega L, and a capacitor is minus J over omega C. When I convert those to the phasor domain, and this omega is this number right here. It's the 200 pi. So that's where the 200 pi will show up in your circuit, is in your inductors and capacitors. Okay, and then our second one, which is 120 cosine 377 t minus 60 degrees. Well, this one could not be any easier. It's 120 angle negative 60 degrees. There's nothing else of the following quotient. So there are different ways of doing this. One way is I could change the top to polar and the bottom to polar, and then I could combine. This is where I mess up because I'm going to do it different than I did in my notes. I can't help it. Okay, I'm going to do this one different than I did in my notes just to teach y'all something new. Okay, so I'm going to change the top to polar and the bottom to polar. So when I change the top to polar, I will get the square root of 64 plus 36 angle inverse tangent of negative 6 over 8. Now let me think about where that's going to be. That's going to be in the real part is positive, the imaginary part is negative. That's in the fourth quadrant, so it's fine. I don't have to change anything on that. Over the square root of 4 plus 25 angle inverse tangent of 5 over 2. So let's do all of that. So square root 36 plus 64 point is 10. So that's 10. Oh, I knew that. Angle negative tangent, inverse tangent of negative 3/4. Inverse tangent of negative 0.75 is negative 36.87 over square root of 4 plus 25 point is 5.39. Angle inverse tangent of 5/2 is 68.2. Now, remember, these are shortcuts for exponential functions. And what do you do with exponents when you divide? You subtract. So the numbers in front, we will divide them. That'll be 10 over 5.39. And our angle is negative 36.87. Was that an 8? 87 minus 68.2. So 10 divided by my 5 is 1.86. And then angle minus my other angle is 105, negative 105, angle negative 105 degrees. And that is easier than the way I did it on my notes. Yes.
So, I think, so the first part of the fraction, a minus j6, I assume that's in quadrant 2, right?
That is in quadrant 4 because
Oh, yeah,
it's,
quadrant 4, okay.
yeah, so that's the real and that's the imaginary. So that's what I drew right here.
I was confused because I was like, why did you add or?
Yeah.
Thank you.
Okay, so what this means is whenever you have numbers in polar form, so if I have 5 angle 30 times 2 angle 10, that's easy. That's just 10 angle 40. When you multiply, you add angles, and when you divide, you subtract angles. That's why polar form is easy when you are multiplying and dividing. All right. And the next one is super easy. This is, what's 5a? 5 angle 20. Nothing to it. What about b? 10 angle negative 140 degrees, which is not smaller than negative 180, so I don't have to deal with anything there. And I think I'm going to stop here. The other problems on this worksheet would be good practice problems for you to do, and I will just tell you what the answers are, and then you can do them and check yourself. If you have problems, you can come and ask me. Yes?
For this question 5, how are we able to just look at it and just get the answers?
Oh, because we're all magic. We just haven't told you, yeah. So here's how we did it. So when you have a cosine function, the number in front of the cosine, unless it's negative, is your magnitude. We don't worry about this part, and this part is your angle. If it's sine, that's still your magnitude, and you subtract 90 from your angle. So if I had 30 sine omega t, whatever omega is, plus 60, I know that would be 30 angle negative 30 degrees, because I just subtract 90 from it because it's a sine. Negative angle. So let's say I had negative 3 angle 30 degrees. Okay, so what you want to think about with that is that it's 30 degrees, but in the opposite direction from that. So it's 3 in this direction. And so we would want to go around this way and get negative 150 degrees. So that would be 3 angle negative 150. So you want to either, I wonder if you're ever going to add 180. Let's see, if I had negative 2 angle negative 130 degrees, then that would be negative 130 degrees, yes, and so then I would add 180 to get to that one. So that's how you do it. Okay? So when you have a negative magnitude, then you either add or subtract 180 degrees to get it into between the negative 180 and positive 180. Thank you. Thank you for that correction. Other questions? Yes?
Could you do just a more quick explanation of how to go from phasor to rectangular?
Sure. Okay. So phasor to rectangular. So I have one thing you can't get with just a phasor is the complete time domain. You have to also be given the frequency, because the frequency is not there. So let's say I have V angle theta. So those are just numbers. Then what this is going to be in rectangular is V, open parentheses, cosine theta plus J sine theta. And then you just have to find out what that is. So if I had 25 angle negative 30 degrees, that would be, well, let me do negative 45 degrees. Negative 45 degrees. That would be 25 open parentheses cosine negative 45 degrees plus J sine negative 45 degrees. And that would be 25 times 0.707, because that's the cosine of negative 45 degrees, minus J 0.707, because that's the sine of negative 45 degrees is negative 0.707. And then you multiply that by 25, and I'm out of tricks of doing it in my head. But what we were just talking about, what would you do if you had negative 6 angle 20 degrees? Okay, so what you want to think about for that is, are you going to add 180 or are you going to subtract 180? Because that's the way you're going to get rid of that negative sign. And so if I added 180, I'd be over 180. So I subtract 180 and I get 6 angle negative 160 degrees. And then I would have 6 times cosine negative 160 degrees plus J sine negative 160 degrees. And then you just do those. Other questions? And polar on the, you actually have an older 84, I think, which means that yours is going to work better than a newer 84. That one might actually do polar for you better than the newer 84s. If you want me to check it out, I'll check it out when we're done. All right, so I'm going to stop this, and I want to take